pleased to introduce our speaker today, Dr. Bonnie Ludka from California State Polytechnic University in Humboldt. Bonnie is a coastal scientist with a background that spans physics, oceanography, geology, data science, and engineering. They're interested in how coastal physical processes interact with environmental management and ecological functioning on timescales from storms to decades. Bonnie got her PhD in the physical oceanography department at Scripps, and she's held postdoctoral positions at Scripps, as well as Delft University of Technology in the Netherlands. They were also a California Sea Grant Fellow and a California at the California Coastal Commission. Unfortunately, Bonnie has just left San Jose State to join the faculty at Cal Poly Humboldt, but she is collaborating with us on some work in Elkhorn Slough. So we're hoping to keep them involved in research in Monterey Bay. So with that, thank you for joining us, Bonnie, and let's welcome Bonnie. Thank you.
Thanks so much, Tom, and thanks everyone for coming. I'm delighted to be here. And today I'll be talking about wave-driven changes in beach sand levels. Okay. So I'm Dr. Bonnie Ludka, and this is work that I have done at Scripps and continuing on in my new positions. And I want to acknowledge all the fantastic co-authors that have been involved in this work, as well as the Scripps field crew, who really keep the beach surveys going and operating, as well as the CDIP team. That's the folks who maintain the wave buoy network that we use and the model and make those data available for us for what I'm about to show you. And I'll also acknowledge our funding agencies: National Science Foundation, U.S. Army Corps of Engineers, California State Parks, Boating and Waterways, California Sea Grants, and NASA. Okay, so you all may not need so much motivation since this is a sort of coastally located ocean crowd, but just in case, why should you care about beach sand levels? Well, beach sand levels can protect coastal infrastructure or predispose. Similarly, sand levels can protect or predispose coastal infrastructure to erosion. So for example, you have a narrow beach that allows the waves to undercut a cliff that can predispose the cliff to erosion. And in this case, the cliff failed and this home that was on top of it failed along with it. Beach sand levels can also influence coastal tourist economies. There have been studies that show that the width of the beach can be related to the strength of the tourist economy. Your tax dollars are used to engineer beach sand levels. So this is a picture of sand that is being placed on Cardiff Beach. And we'll talk about beach replenishment later in the talk. And beach sand levels can also influence important groundwater and ecosystem services. The schematic on the left is showing the wide beach and the location of the boundary between the fresh groundwater and salty groundwater for that wide beach, as compared to where that boundary moves with the narrowing of the beach. And this is of concern, especially in places where there are limited fresh groundwater supplies, like low-lying islands, where they're worried about saltwater intrusion of their fresh groundwater supply due to storms and sea level rise. On the right, I have an image of a western snowy plover. As you all are probably familiar with this bird, but it requires beach habitat for nesting, and there are a whole host of organisms that depend on the beach, and we in turn are getting many ecosystem services from the beach. Beach sand levels are an international issue, as 1 billion people live within 10 meters of present sea level. That population is increasing drastically, and sea level is rising. Okay, so for an outline of the talk, first off, we will chat about equilibrium beach profile evolution. Then we'll talk a bit about sand replenishment, also known as beach nourishment. And I think I actually don't have time to talk about satellite assessment of storm-driven coastal change, but I just wanted to show that that is some other stuff that I have been working on previously. And the two sections of the talk that we'll get to are using data sets from San Diego. The satellite work is being done in the Bahamas. And we'll have a little nearshore anatomy lesson here to make sure we are all on the same page. So here's a beach profile, and the nearshore is defined as running from the back of the beach to offshore, and how far offshore, it really depends on who you ask, what kind of oceanographer you ask, how far offshore the shore goes. And for me, the nearshore extends just beyond the surf zone, so that region of breaking waves. The shoreline is where the water level meets the beach, that location there. And you're probably familiar with the word topography. So this is the elevation of the beach on the part of the beach that is above water. And bathymetry, you're oceanographers yourselves, and that's the underwater elevation of the beach. And the subaerial part of the beach, you'll hear me say that word a lot. Subaerial means beneath the air. So that is when I talk about the subaerial region, we're talking about topography. And we've got the subaqueous, beneath the water, bathymetry. Okay, so now for a coordinate system, we've got surf zone and subaerial beach here, and the cross shore direction runs between them. And perpendicular to that is the alongshore direction. All right, so how do we measure sand levels? Well, we have a few different techniques. We use an all-terrain vehicle, or an ATV, and we drive that at low tide on the subaerial beach. We also use a jet ski that is equipped with acoustic sonar, and we drive that at high tide. But often there is a gap between these two data sets, so we need to fill that in with, we usually use this push dolly, then we push that into about chest deep water, and that's me pushing the dolly to get this part of the profile that we couldn't capture with the ATV and jet ski. And this is really where the really hard work is, because you're pushing this contraption into sometimes very strong currents and decent waves. And yeah, so there's a lot of effort that's gone into collecting this data set. All of these vessels and vehicles are equipped with GPS. And an example of what one of these surveys looks like is on the left here, where the rainbow colors are showing you elevation relative to mean sea level. We've got land on the right, ocean on the left, and I've also colored in reefs, rocky reef locations in black. A submarine canyon is shown in brown there. And this data set has been published in Nature Scientific Data. There's about 16 years of this data, and it's available if you are interested. And this example survey that I'm showing you is from Torrey Pines, which is our longest running data set, and also the longest, well, that's not true. It's along a longshore stretch of beach that runs about, this is about 8 kilometers of beach here. Okay, and now what we have is what I call a LiDAR revolution, where the ATV has been replaced with a truck that has a scanning laser mounted on top of it. So this is our LiDAR, and we use that to measure the subaerial beach. And this is an example of what that data looks like, and you can see that it is incredibly high resolution. We can see ripples of sand on the beach, and we're not only getting the beach now, we're able to monitor the cliffs as well. And here's another fun, this is data from the LiDAR itself. where we did a survey during one of our field experiments, and we captured our trucks and field crew and grad students and postdocs all on the beach here. And you can just really see the amazing quality of this data set. We also have a LiDAR drone that we use to measure the subaerial beach. I sometimes will use LiDAR data from airplanes as well, which sometimes measure the subaerial beach, but sometimes these airplanes also can be equipped with a green laser that actually can penetrate the water column and measure bathymetry. And most recently, there has been a satellite that has been launched, ISAT-2, that is also equipped with a very strong green laser that, to many people's surprise, can also capture bathymetry in clear waters out to about 40 meters depth. So that's really exciting as well. So some really cool data sets here. But in order to understand what the sand levels are doing, we need to know what the waves are doing. So for wave monitoring, we use the CDIP buoy network, and this is a schematic of sort of an example of how the buoys can be distributed in the Bight, the Southern California Bight, where the red dots are showing the locations of the buoys. And these are what the buoys look like being deployed. And so those buoys are then used to initialize a spectral refraction wave model. And this image on the right is showing you in color an example of significant wave heights on this particular day. And you can see there's quite a bit of alongshore variation on our coast due to island shadowing and shoaling across complex bathymetry. So it's really important for us to have these observations and model in this particularly complex region. And these buoys and model combined give us hourly wave estimates every 100 meters along shore in 10 meters depth. All right, so what have we done with these really cool data sets? Well, first off, we'll talk about equilibrium beach profile evolution. And so for a little bit of context, in Southern California and many beaches elsewhere, our beaches rock sort of between a summer sand berm and a winter offshore sandbar. And they rock back and forth between these two states. But we want to understand how the beach profile, how that rocking responds to instant wave conditions. And it turns out this is actually a pretty difficult problem because sediment transport in general is a difficult problem. Here, I'm showing actually a slightly outdated, I need to update this reference, but my point is that there is a whole field of physics that is studying the flow of grains and trying to understand how to best model that. So in this case, this is an entire review article about all the different experiments and modeling that have been done on looking at uniform spherical grains. They're all the same size and they are flowing under gravity down a unidirectional chute. So a very sort of simplified experiment, and the colors on the right are showing model output. This is a non-dimensional velocity that you're seeing, but point being that there is a whole field of physics surrounding these kind of scenarios, which means that this scenario is a really, really difficult problem, which means I have great job security. This is a situation where you have grains of many different shapes and sizes, and they're being moved around by waves that are nonlinear and random and turbulent. So this is a pretty difficult task. And there's a few different approaches you can take. One approach is to assume some physics first, because we really don't know, we don't have like a Navier-Stokes equation equivalent for sediment, at least not a widely accepted one. And so we can assume some physics first and then test that physics against observations and see how we do. Another approach is to look to the observations first, and then use statistical insight to develop new models. And so both approaches are valid. In this case, what I've done is more in line with approach number 2. So we're going to look to the observations first and use some statistical insight to develop new models. And so what we did when we first set out to do this was we were interested in testing the equilibrium hypothesis, which is that under steady wave conditions, a beach will evolve toward a unique wave condition dependent equilibrium beach profile and will experience no further change after equilibrium is reached. And so what this means in cartoon form is that if you have some hypothetical beach profile and some hypothetical offshore wave conditions, for those wave conditions, there is a particular equilibrium beach profile that this beach evolves to at first rapidly and then ever more slowly. Then for some different set of offshore wave conditions, there is a different equilibrium beach profile that this coast evolves to at first rapidly and then ever more slowly. And this idea has been around for quite a while. The canonical reference is Per Bruun, 1954, but Bruun recognized that folks had been equilibrium hypothesis. It's been around for a while, and Bruun recognized that other people had come up with it even before he did. But what we're doing that is unique is that we are the first to set out to test this with observations of the beach profile. Okay, so we're going to do that with this sand level data set, which was the jet ski, dolly, and ATV data. And this is an example of what one of those surveys looked like. And we did this at the 5 different sites along the Southern California coast. And we used these surveys that were done about 4 times a year that extended from the back beach out to about 8 meters depth. And the data set that we had at the time at all these different sites, we had a few years of data, with the longest data set being 10 years at Torrey Pines. And what I did was I broke the coast up into about 800-meter chunks. And that's what these little black boxes are. And then I alongshore averaged the beach elevations in that region to get a time series of beach profiles. And then I also decided that I didn't want any of these sections of beach that were kind of complicated. So I threw out the sections that had rocky reef or submarine canyon. And I just stuck with the parts of the coast that I consider sort of normal sandy sites. And a site that I call T8 is one site that I'll be showing you throughout the next few slides. So if you'd like to keep that in mind, that's where this one is. And again, we're setting out to test this equilibrium hypothesis, and we're the first to test this idea with observations of the beach profile. And in order to do that, we need to quantify, we need a way to quantify the shape of the beach, to put a number on the beach state. And to do that, we are going to use empirical orthogonal function analysis, also known as principal component analysis. Those things are quite similar. In the oceanography world, folks tend to call it empirical orthogonal function analysis. So that's what I'll do. I'll also refer to it as EOF analysis. And so what this is just a statistical method to identify the dominant patterns in the data set. And in our case, we're just going to focus on the mode 1 EOF, which is the mode that explains the most variance in the data set. So that dominant pattern in the data set. And in our case, at all of those sort of normal sandy sites, the first mode EOF explains more than 50% of the variance at all those sites. So we feel confident that this really is truly a dominant pattern on our coast. And in order to do this analysis, what we first do is we've alongshore averaged all those sections of beach to get a time series of beach profiles. And then what we're going to do is we're going to subtract out the mean profile to get a beach elevation fluctuation. So here I'm showing an equation just showing that we've got our beach elevation Z, and we're going to subtract out the mean to get a time series of beach elevation fluctuations. And then the UF reconstructs this time series that is also spatially varying. And it does so using a spatial shape function. And what this function is telling us is that when the upper beach is accreted, when you have that berm, the offshore region is eroded and vice versa. So it's a rocking between the berm and the bar. That is what that function is showing us. So this axis here is cross-shore distance. And this is just showing the relationship between the berm and the bar. The EOF also tells us how the beach behaves in time, and that is encapsulated by this middle plot called the beach state, or I'm calling it the beach state, is the temporal amplitude of the EOF. And so what this tells us is throughout the year, when is the beach in that berm state and when is it in the barred state? So for example, at this time where I've highlighted in the red dot, that is a positive value that is representative of a beach in the berm state. If we multiply that red dot value by the spatial shape function and we add back in the mean, then we get this reconstructed berm profile. Similarly, if we look at the next survey during the winter, when the beach was in a barred state, we take that blue dot, multiply by the top, add back in the mean, and we get this EOF reconstructed barred profile down here. And in fact, the EOF reconstruction is plotted on top of the actual observations, and they're right on top of each other in this case. So again, the EOF does a pretty good job here. And I should say that we're actually not the first to do an EOF analysis on these beaches. Clint Wynant and friends did this back in 1975. And many others have also used this technique. What we are doing that is novel is that we're going to take this analysis and then we're going to take it another step further. So again, at all of those sandy sites, we do this EOF analysis, and we're going to use the temporal amplitude, and we're going to create another analysis from this temporal amplitude. And we're going to create this scatter plot. So I will walk you through it. And so what this is showing is that for each consecutive pair of surveys in our beach state temporal amplitude, we take that beach state temporal amplitude, those consecutive surveys, and we use those to make the scatter plot. So on the x-axis, we take the initial beach state of those consecutive surveys, and we plot that on the x-axis. The y-axis shows us the average wave energy that occurred between those two surveys. Then the colors are showing us the beach state change rate that occurred between those two surveys. So we are seeing, for our x-axis, we're showing barred profiles on the left, then and initially bermed profiles on the right. So that x-axis is the initial state of the beach. And the colors, the red is showing when the beach changes toward a barred profile, and the blue is showing when the beach changes toward a berm profile. Now let's think a little bit more about what this means. So when I first got into this business, I think I would have thought that, okay, well, big waves, they always erode the subaerial beach, you know, like that's got to be how it works, right? So I would have thought that that anytime you have wave energy that is large, so sort of the top of the graph, I would have thought that you would always see sand moving from the berm towards the bar, so a change toward a barred profile. And in calm waves, I would have expected the opposite. But in fact, that is not what we see here. Instead, what we see is something more consistent with the equilibrium hypothesis. So let's think about a scenario. So say you have some incident wave energy of about 0.062 meters squared. That's consistent with a wave height of about 1 meter. So sort of moderate wave conditions. And so say those waves are incident on a beach that is initially already in a slightly barred profile. Well, that beach will change toward a berm profile, which looks like this. Okay, so that initial beach changes towards a berm profile. In a different case, you have those same offshore wave conditions, but a different initial condition. So you have a initial beach state where that beach is slightly burned. But in this case, you see that the beach behaves in the opposite manner. The beach will change toward a barred profile. So you have the same offshore wave conditions, but a different initial beach state and a different behavior of the beach. So what's actually happening here is this beach profile is evolving toward an equilibrium profile. So that is what our scatter plot, we think, is showing us, is that this is evidence of the beach profile evolving towards equilibrium. So observational evidence for equilibrium beach profile evolution. So we were really excited about this. And we asked ourselves, okay, well, how can we use this to make a predictive model? So we defined a equilibrium wave energy. So this is the wave energy. So if your beach is in some particular state, this is the wave energy that would not change the beach at all. And we define that equilibrium energy as a linear equation relative to the beach state. And we choose linear just because we want to keep it simple. That's the main reason as we were designing this. And there are, and then we said that our beach state change rate is not only dependent on the incident wave energy, but also on this wave energy disequilibrium. So this really determines the sign of the beach state change rate. So in the case where you have an incident wave energy that is less than the equilibrium energy, you will see a change toward a berm profile. In the case where your incident wave energy is greater than the equilibrium energy, you'll see a change toward a bar profile. We have a few free parameters in this model, 2 for the equilibrium wave energy and another for the change rate coefficient. And I just want to mention that we actually don't get these values from this scatter plot because the scatter plot that was our sort of motivation for the model framework, but the surveys that we are using are spaced, a month or many months apart in time. But we are really interested in trying to be able to resolve storms, and we have hourly wave conditions. So we want to see if we can use this model to with a shorter time scale. So to do that, we run the model forward a bunch of times and find the optimum values that match the data set. And we use this nonlinear optimization scheme. But basically what I want you to know is that these parameters are optimized for hourly wave energy. So we are trying to take into account storms. I do want to say that this framework, we didn't come up with it on our own. Yates and friends used a very similar framework, but they were just thinking about the position of the shoreline. Here I've extended those sort of ideas to the entire beach profile. And Yates also very much Yates and friends based their work, was very much inspired by Wright and Short's work in the 1980s. So of course, as always, standing on the shoulders of giants. And okay, well, how does our model perform? So in the top panel, what I'm showing you is a time series of wave energy. You will notice that we get bigger waves in winter and smaller waves in summer. And the observed waves are in blue, and the modeled equilibrium energy is in red. So anytime the observed energy is higher than the equilibrium energy, you expect change toward a berm profile, and anytime the observed wave energy is lower than that equilibrium red line, you expect change toward, sorry, did I say that backwards? When it's higher, you expect change toward a bar profile, and when it's lower, you expect change toward a berm profile. Yeah. Okay. So in the bottom plot, you have a time series of beach states. So this blue time series is extracted from that first mode EOF from the temporal amplitude, where the positive values are showing a beach in a berm profile, and the negative values are showing a beach in a barred profile. And the red is our model. And in sort of sediment transport land, we think that this model actually behaves quite well. So we were pleased. We thought that was really cool. And we tested this. So that was an example at T8, that section of Torrey Pines that I pointed out at the beginning of this section. But we also tested this at all those other normal sandy sites and found that the model had high skill and low normalized mean square error at all those sandy sites. And I will say that we tested how much calibration that the model needed in order for it to have a skill like this. And it needed about 2 years of calibration with the sort of seasonal survey frequency that we had. And this is published in JGR and was part of my graduate work. So it'd be great if you're curious, feel free to check that out. And to recap, we found field evidence for beach profile evolution toward equilibrium. And we found that an equilibrium framework well models the temporal variability of the beach profile state in Southern California. I will say that, the model isn't perfect. It often overpredicts extreme erosion because it kind of assumes the beach is infinitely erodible. It doesn't know that there's bedrock there or cobble there. We have sort of played around with putting in an erosion limiter based on where we do know that some of the harder substrate is, and it does improve model performance, but you need some of that site-specific knowledge for that. The model also fails where the first mode EOF fails. So at any of those, rocky reef sites, submarine canyon, even some of the mid profile where the first mode doesn't capture that much variability, the model doesn't do that great. And we played around with using higher modes and complex EOFs and all that if you have folks that are nerdy about that stuff. But anyways, that's in the paper. And I just want to say that it's a cool model. It works pretty well by sediment transport standards, but it has its limitations. Okay, so how is this model being used? Well, for one example, it is being incorporated into a flood forecast. And okay, so here I'm told that this video is a little bit choppy, but what you're maybe seeing is that this is flooding at a site called Imperial Beach in Southern California, which experiences some significant flooding, and it happens fairly often, sort of moderate high tides, moderate energetic waves, and the waves overtop this riprap and go into the streets. And there are folks that I've had the privilege of working with to develop this flood forecast. Whoops, I didn't want to play that again. How do I, there we go. Julia Fiedler has done a lot of work on figuring out how best to model the run-up here. And then Mark Merrifield and colleagues have also been developing this operational flood forecast system. And you can check out the flood forecast on their website here. That website is maintained by Melly Johnson, where you have the observed conditions, wave conditions, and the forecasted. And anytime that those bluish colors get above that red flooding threshold, that's when the city gets alerted that they may be getting wet there. So incorporating the beach, we hope this beach model like this will hopefully improve the flood forecasts. And this is a sort of a nice transition to the next topic, because you could imagine that the folks here might want to try to protect their homes. And in fact, there was a large sand replenishment project that was done here to help prevent flooding of these homes in Imperial Beach. I have been using the term sand replenishment because I think that is a terminology that is maybe a little bit more intuitive. I have no idea why beach nourishment is called this, but it is. So you'll also now hear me call this practice beach nourishment. This is where sand is taken from off-site. In this case, it was taken from offshore and is placed on the beach. And this aerial image here is showing you the mechanical placement of sand at Imperial Beach, where you can see some bulldozers moving that sand into place. And you see the narrow, unnourished beach in the background there compared to the wide, nourished beach in the foreground. And in this case, the volume of sand that was added was around 300,000 cubic meters. And for context, because I always, need some sort of visual, that amount of sand would fill up 120 Olympic-sized swimming pools, approximately. So it's a decent chunk of sand, and it was placed in 2012 and was the largest of 8 nourishment projects that were all done around the same time in Southern California. The total cost of those 8 projects was about $30 million. And this was just one of 4 projects that we monitored. And I have some work that compares those different projects in GRL and coastal engineering. And if you're curious about what happened at those other sites, you can find that there. But today I'll just be talking more in depth about what we saw happening at Imperial Beach, which was, again, the largest nourishment of all of the ones that we studied. Okay, so for the work that I'm about to show you, the sand level data set that I used was all subaerial data. So we're just looking at the subaerial beach for this analysis, and we used truck LiDAR, airplane LiDAR, and ATV LiDAR. And we used 13 years of, in this case, monthly subaerial surveys. And we are looking now at a 10-kilometer stretch of beach surrounding Imperial Beach. And what I've done here is I've outlined in orange a region around the nourishment placement, which kind of shows the view of this aerial photograph. And these red dots are showing the extent of where the nourishment was placed. This image was taken sort of mid-placement. And I'm also showing where the location of some sand retention groins are. Sort of local folks say that these groins don't actually trap much sand, potentially because they're fairly short, and also potentially because currents are weak there. The star here is marking that location of flooding that you saw in the earlier video. And Seacoast Drive is this street that often floods from a number of places along the stretch of coast. But this starred place, Cortez Drive, is where we were looking at earlier. And then also south of the nourishment placement region is the Tijuana estuary. And that I will talk a bit more about on the next slide. So the Tijuana River estuary is a really complex place. It is ecologically rich. There are a number of endangered bird species that live there. And if you visit there when it has not rained, it's really stunning. And it's really an amazing preserve. If you go there after it rains, it's incredibly polluted, and that pollution flows into the estuary and out of the mouth and into the ocean here, which is one of the reasons why we don't have a lot of offshore data here. It's just not safe for us to get in the water as much on our jet ski. And in fact, if you ever go there and you're hanging out there after a recent rain, do not get in the water. You can get very sick. So a complex place. And also the Tijuana River mouth has closed in the past. Here is a LiDAR survey, or actually a group of LiDAR surveys I'll show you, and the river mouth migrates. And in 2016, the river mouth closed, and the closure had to be dredged, mechanically removed. And before that dredging was able to happen, the estuary became hyperpolluted, it became hypoxic, and a bunch of critters died, including these are dead leopard sharks, unfortunately, that were pulled out of the estuary during the closure event. And there are folks locally who think that this closure may have partially been may partially be because of the nourishment sand that was placed north of there. But that's kind of one of the questions that we were interested in answering. So we know we have these low-lying homes that are vulnerable, and there was sand placed in front of them to prevent flooding. And you also have this issue of river mouth closure. And how can we assess the impact of the nourishment? Well, we need to monitor those sand levels and waves and track where things went. So how did the beach evolve after nourishment is really the question that we are after. And so, well, first, right off the bat, we can see that there is definitely still nourishment on the beach. There's nourishment sand on the beach. It's still there, even this plot's, showing to 2020. So 7 years later after nourishment, where what you're looking at here is the alongshore integrated subaerial volume of sand. So this black vertical line is showing when the nourishment placement occurred, and you can see a jump in the time series, so a jump in that sand volume after placement. And I've also labeled in gray here the El Nino winters, which is when, as you all probably know, we have repeated energetic storms that tend to erode the beach, but the sand levels remained quite high. The volumes remained high even after the 2015-16 El Nino on this stretch of coast. And this is different from what we observed at some other sites. For example, in 2001 at Torrey Pines, the nourishment that was placed there was effectively all washed offshore in like a single storm. And so this is very different. And in previous work, we showed that the main characteristic of the nourishment that was responsible for it staying on the beach for so long was that it was a relatively coarse-grained nourishment. So it was constructed with a median grain size of about 0.6 millimeters as compared to the native grain size, which is about 0.2 millimeters. And that work of sort of sussing out why the nourishment remains subaerial for so long is done or is shown in our GRL and coastal engineering articles. And we really did try and suss it out, even though, wave conditions may be different across sites or across times. And this really stood out as why that sand was still there. But now we want to think about, okay, well, we're looking at this whole region sort of in bulk, alongshore integrated. Now I want to think about, okay, well, where did the sand go sort of within this region? And we found first that, actually, before I tell you what we found, let me tell you how we approached figuring out how the sand moved in the alongshore. We broke the coast up into much smaller alongshore chunks, so 100-meter alongshore chunks. And so first, let's look at a 100-meter alongshore chunk of sand volume in front of Seacoast Drive. And this is the time series of subaerial volume in front of Seacoast Drive. And you can see that there is a jump in the time series after nourishment. And if we look at the change between the average sand volume before and after nourishment, we didn't plot it. Anyways, we see that it's a positive value, a positive jump before and after nourishment. And also down by the river mouth, we also see a positive jump in the mean value of the subaerial volume before and after nourishment. And if we plot those values all along this coast, we can see that we have a positive jump in the subaerial volume from about the river mouth to the groins. So we sort of sussed out the extent of nourishment influence is between the river mouth and the groins. Then we also looked at sand volume trends. So before the nourishment, so we're just looking at this time period on the left-hand side here. So before the nourishment, we saw that the sand volume in front of Seacoast Drive was eroding. So we see this sort of red shade of our trend line here. And down by the river mouth before nourishment, we saw that those sand volumes were actually increasing. That's denoted by this sort of green color here. And if we plot that all along the coast, we see that there's sort of this erosion signal in the vicinity of Seacoast Drive and some accretion happening near the river mouth. And then if we do the same thing after nourishment, we look at those trends, we see very significant erosion in front of Seacoast Drive, perhaps not surprising because that's where the nourishment was placed. I've drawn the nourishment here with this black outline. It might be small, but it was placed in front of Seacoast Drive. Saw a bunch of erosion, probably because that beach was out of equilibrium with waves, but also tends to be a place of erosion we find. And then down by the river mouth, we see this large accumulation of sand, which, you know, was not predicted when people designed this. Okay, so what we found by looking at these sand volume trends is that both before and after nourishment, sand eroded in front of Seacoast Drive and accumulated on the north side of the river mouth. And so we wanted to know, well, why is Seacoast Drive an erosion hotspot, and why is sand building up on the north side of the river mouth? Well, our hypothesis is that, you know, we know that waves carry momentum, and when waves arrive at the coast at an angle, momentum is transferred into alongshore currents. And we're going to use this quantity called the radiation stress, which describes the excess flux of momentum due to waves that forces alongshore currents. So we're using this radiation stress as a proxy for alongshore currents. And then those alongshore currents drive alongshore sand transport. So they drive drift. And where we see currents converging, we tend to see accretion. And where we see currents diversion, we would expect to see erosion. And again, we can relate that to the radiation stress gradient, which we often call divergence, a proxy for the divergence of the drift. Okay, so let's look at how our wave model of these alongshore currents would predict what would happen here. Well, it turns out we see what we might expect, which is that there is a divergence of the currents. Currents are moving away from each other. The alongshore currents are moving away from each other in front of Seacoast Drive, and they are moving towards each other near the river mouth. And while this might be, you know, something that you expect from you know, what has been known about how alongshore currents behave, we're actually the first to observe this pattern for a common nourishment. And that might be due to a number of reasons. One might be because these nourishments are not very well monitored, and we have this really excellent data set. Also, this nourishment tended to stay on the beach for quite a while. It was, you know, had that subaerial persistence so that we could track it. And also there's some fairly strong gradients in the alongshore wave patterns here. So what causes that alongshore variation in waves? Well, here at Imperial Beach, if you look farther offshore, so here is, I'm showing the bathymetry out to about 20 meters depth. There is a feature, we're calling it a relic shoal. It's mostly made of cobble, and it actually goes even farther offshore than this. And what we can see is here I've plotted the that proxy for the alongshore gradient of currents, and you can see that that shoal really creates these strong alongshore gradients in currents along our coast. And one of the questions that this raises is that you know, the angle of the waves as they approach the coast is what drives those alongshore currents. So is this coast actually, is it being held in place by some of this riprap and some of these other structures here? And if the coast was allowed to naturally meander, would these hotspots persist? We don't know, but it is a question of interest as to whether or not some of this shoreline stabilization is causing some of these hotspots. We are also wondering, should Seacoast Drive be, nourished every 10 years if, you want to protect those homes? We can see in our volume time series in front of Seacoast Drive, the sand levels are almost as low as they were pre-nourishment now. And if you did that, would that mean that your river mouth would close more frequently? And of course, the evolution of the nourishment depends, on grain size and the waves and all that. But this is just sort of the many different factors that need to be considered in coastal management of this area. So to recap this project, we found that much of the nourishment remains on the subarrial beach, but the area of influence is really predominantly just between the river mouth and the groins, at least for the subarrial beach. And we found that this divergence of the drift causes erosion hotspots at Seacoast Drive, an erosion hotspot at Seacoast Drive, and an accretion hotspot on the north side of the river mouth. And the lifetime of the coarse grain nourishment in front of Seacoast Drive is about 10 years, although nourishment sand, remains on the beach elsewhere, especially down near that river mouth where it may have contributed to river mouth closure. And so this work, I think really nicely displays the difficult task that coastal managers have. And it inspired some work, inspired me and another colleague, Macho de Schipper, to lead this interdisciplinary beach nourishment review. Another thing that happened at that Imperial Beach site was there was some groundwater flooding that may have been exacerbated by the nourishment. As many of you know, there are questions about what, many folks don't want to nourish a beach with coarser grain sizes because of the ecological impacts. So there is a lot of issues that play out in terms of managing beaches with beach nourishment. And we put this literature review together for Nature Reviews Earth and Environment. And it's really for kind of a coastal management and interdisciplinary audience. So that might be one of the better papers for this audience to read if you're interested. And it was an international collaboration, which also made it neat. And we also discussed sort of social implications of nourishment and identified future research and engineering design priorities. I don't have time to talk about the satellite stuff, and I just really quickly want to say a few things about a fun collaboration that Tom Connolly and I have with another I'll leave the highlights up at the end to summarize. But yeah, so I am interested in sort of expanding into different flavors of coastal research. So a lot of what I've done has been focused on beaches, but I am now excited to start, moving into estuarine systems and other systems. So Tom has been a really awesome collaborator, and he and I and Dr. Mara Oreskinen got a San Jose State Level Up grant to look at what is causing salt marsh erosion in Elkhorn Slough. And I think you all are, many of you have projects there too. So would love to hear your thoughts on this. And this is an area that I am just starting to get to know, coming from Southern California, but I'm excited to do more work here. I was up or down that way this summer for some preliminary work with Tom and Mara. And as you all know, salt marsh is important because it provides critical habitat, sequesters carbon dioxide from the atmosphere, reduces flooding and erosion, improves water quality. And salt marsh habitat is threatened due to urbanization, agricultural runoff, and sea level rise. And in Elkhorn Slough, quite a bit of salt marsh habitat has been lost over the years. And this is an image from Van Dyke and Wasson showing, the salt marsh is that sort of brightish green color. And you can see that much of that has been reduced between 1913 and 2000. And this was supposed to animate. It's a little overwhelming as it's shown now. But we are testing this hypothesis that potentially the harbor construction is what is inducing some sort of runaway erosion processes. This was introduced by Brockenkow and Brecker. I may be saying that wrong, apologies. And the harbor was constructed back in 1946, which we think exposed the estuary to more energetic tidal currents. And this is an ebb-dominated estuary where you have more export of sand going out than coming in. So if you have increased tidal currents, you have an increased tidal prism, so you have more water flowing into the estuary between low and high tide, which further increases the currents and potentially further increases erosion. So this is a hypothesis we're trying to test using a field experiment and some numerical modeling. And we've been out on the boat a little bit, and we'll be getting observation. We'll also be deploying a mooring, and we'll have observations going of bathymetry and potentially sediment samples and currents and water levels and turbidity, temperature, salinity, dissolved oxygen. We're interested in interdisciplinary questions as well here, and this will be work going towards a larger NSF proposal that this level up grant has lined us up for. All right, so I'll go back to my summary slide here. And thanks for listening. We talked about equilibrium, beach profile evolution, and beach nourishment, and a little blurb on some of the work in the estuary of Elkhorn Slough that I'm doing with Tom. I think I ran over a bit, but thanks for your patience. I'll take questions if folks are still there.
Okay, thank you, Bonnie. I think we'll go into questions now, and I'll be trying to monitor both the Zoom chat and the questions in the room. Okay, and well, we have a question from the room.
Hi, Bonnie. Oh, thank you for the presentation. That was awesome.
Yeah.
I had a question about the size of the sand. You were saying that there were possible adverse effects on the ecosystem with those coarse grains. So I was just curious if there was a particular reason that size was used, as far as for the success of the project, or maybe it's not eroded so easily.
Yeah, I think they did use it with the intention of keeping the sand on the subaerial beach longer. I worked at the Coastal Commission, after that happened, and with sort of having worked at the Coastal Commission and seeing the approval of other nourishment projects, there's part of me that is a little bit surprised that the coarser grains were allowed. But like I said, coastal management is balancing, many different factors. So I wasn't at the Coastal Commission when that discussion was happening. So, but I do think it was with the intention of increasing the retention of the sand on the beach, potentially because the previous nourishment that was done in that region in 2001, it really didn't last very long at all. So I don't know the answer to that, but I think that it was for retention.
Okay, and Bonnie, I had a question.
Yeah.
Okay. The sand near the mouth. So did you observe any of that coarse grain sand from the nourishment at the river mouth itself?
Yeah, we did. We had sand samples, and we saw the coarser grains down there. So that was actually a nice way to trace the sand. Yeah. And I couldn't hear the very first part of your question, but so feel free to repeat it if I didn't answer it in full.
No, I think you got the main gist of it. So.
Okay, cool.
Okay, I'm not seeing any more questions in the chat or in the room itself. So, well, thank you for that great seminar, Bonnie, and let's give Bonnie another hand.